I'm Adrish.
Hi, I'm Akanksha, and we are It Takes Two. Our project for 6350 is fully differential Class D audio amplifier.
First, we will demonstrate the functionality of our chip. We are feeding the input audio on the left of the PCB through an aux cable. The chip generates amplified differential audio signal, which we then connect to the speaker on the right. Let's go over some of the important signals. So this is the input audio signal. This is one of the generated PWM output signals. This is the two differential output signals which go and connect to the speaker, and this is the difference of the differential output signals. So first of all, as you can see, when the input is static, the PWM duty cycle is almost 50%. Next, now I'll just quickly go ahead and play a sinusoidal tone and see what happens. So as you can see, this is the input sinusoidal signal. PWM gets generated and we see the differential audio output signal, and this is the difference. So as expected, we can see all the signals. Next, I'll quickly play a simple piano tone and let's see what happens. So we can see the different sinusoidal components of the input audio signal, and the output follows the input output signal. Next, I'll play a slightly more complex music and let's see how the input and output audio waveform looks. Again, as you can see, our output waveform completely follows the input waveform, and this is the generated PWM.
So let's go over our testing setup. We are feeding 5 volts external supply which comes in over here, and we have two LDOs on our PCB. We have one LDO over here which is the analog side LDO, and the other LDO is over here which is the switching side LDO. The idea behind dividing a power domain into two parts was to avoid getting any noise from the switching side to the analog side. Okay. This is where our input signal comes in, and we have an aux cable which feeds the input signal, and this is where our final outputs come from, and these are the signals which feed the speaker. We have taken care of routing our left and right channels differentially and in a symmetric manner on our chip as well as on our PCB to get advantage of rejecting the common mode noise which is present in our system anywhere. So this is our surfboard, and on top of the surfboard is the socket in which our chip is present. Over here you can see there are two potentiometers which can be tweaked in order to control the volume of our Class D amplifier. Over here you can see there is a LC filter, and the cutoff of this filter is around 25 kilohertz. The use of this filter is to essentially reject any higher order harmonics coming from the PWM. Over here we have some tone control circuitry, and there are multiple potentiometers over here which help tweak the IREF going into various blocks on our chip, and this essentially helps us control the performance of individual blocks on our chip. For example, the IREF going to the ramp generator helps control the ramp frequency. Over here we are probing the input signal. Over here we are probing one of our output PWMs, and then we are probing two output filtered signals over here.
In this section, we will go over the system analysis and chip overview. The reason to go for Class D audio amplifier is the tremendous improvement in efficiency compared to a traditional Class A amplifier, where the amplifier is always in saturation region. With this architecture, we can get efficiencies in the order of 95 to 99%. what we are doing differently this year is implementing the differential stages using a fully differential amplifier instead of a pseudo differential amplifier, which helps us get better common mode noise rejection and correct for any skews in the two differential paths. Uh, so let's go at the top level system. Here, the first thing we do is convert the input stereo audio signal to a mono signal through an adder. Then that signal goes to a tone control, and then if the tone control block is active, we can control the frequency response of our chip to the input audio signal. Then we convert the signal from single ended to differential using again a fully differential amplifier, and then that goes to our error amplifier, which is this integrator, which is a fully differential integrator. Then the generated differential integrated signal go and feed to these comparators, and the other input is basically a ramp signal. So the output of these comparators are PWM signals. This generated differential PWM signals are then fed to non-overlap generators, and non-overlap generator, what it does is it ensures that there is no shoot through current in the final output stage by ensuring these two the PFET and NFET never turn on together. This helps in not losing out on efficiency due to shoot through currents, and also prevents our final final FET uh, at the same time. And then finally, the generated PWMs and signals are fed to pre-drivers which are suitably sized so that they're able to drive the big uh, switches at the, and the final generated PWM signal is then filtered using LC filters centered at around 25 kilohertz to suppress the higher order harmonics, and then the speaker sees a clean sinusoidal differential input and hence a clean music.
The picture on the right shows our top level layout, and the picture on the left is how our die actually looks. We took a lot of care while making our layouts. The first thing we took care of was to route our right and left channel as symmetrically as possible in order to inject as less as Q as possible in both of our paths, and hence the noise. We also made sure that all our blocks are laid out in a common centroid manner. This gives us as close to as possible performance as the block was designed for initially. Another thing we took care of while laying our devices out were the drivers. The drivers have to pass huge current during the operation of our amplifier. Hence, it is very important to take care of the metal interconnects used in this driver to avoid problems like electromigration. We used only top level metals like metal 8 and metal 9 in order to ensure that as low as resistance is added in our output path because of these interconnects, and as well as to make sure that it is able to carry the high current. We also added a lot of decap cells in our layout. The yellow boxes on the die photo show all the places we added decaps. The decaps help in reducing the switching noise injected in our system due to the drivers and PWM. Over here, we are trying to show how we modeled for our parasitics added by the ESD cell and the package. The two pictures on the right show how we simulated for these parasitics, and the picture on the left is how our chip actually looks. At the center is the small square which shows the actual die, and the outer squares are just our package. As you can see, the die is actually very small compared to our package, and this gives an idea of how much parasitics our package itself can add in our system. So let's go over a few of our key signals. At the very top is our sinusoidal input. Below that is our differential output of the differential amplifier. After that is our integrator outputs, and then is the ramp. After that, we have two of our output PWM signals, and finally, we have the speaker output. On the right, we are showing a magnified image of the ramp and two of our PWM signals. As you can see, the width of our PWM is varying as per the input signal. The table over here shows few of the key specifications we designed a system for. The expected efficiency we designed for was around 95%. The THD is expected around 0.7%. The ramp we designed for a frequency of 500 kilohertz and for an amplitude of around 2 volts. The non-overlap generator was designed for a dead time of 2 nanoseconds.
Over here, we will go over our efficiency measurement setup. We have two ammeters which measure the DC current of the VDD analog path and the DC current of the VDD switching path. This is our testing setup with the chip inside, and the generated sinusoidal output is being fed to a resistor of 8.2 ohms. We are doing a single tone input, single tone output, and measuring the efficiency by calculating the input power due to the analog and switching paths, and the output power by looking at the peak to peak sinusoidal output waveform. And this table is sort of summary of different frequencies of how we are calculating the input output power and output power and hence efficiency. One thing to notice, we also take into account any additional trace losses into our efficiency calculations. So there are two things to note here. Our efficiency is almost independent of input frequency, but efficiency fairly depends on the output peak to peak swing. This is because efficiency or the output losses consist of the conduction losses, the switching losses, and any quiescent currents that any blocks take. So in lower output peak to peak swing, the contribution due to due to the switching losses and the quiescent losses, which are independent of the output peak to peak swing, start to dominate, and hence efficiency drops significantly. This is just a snapshot of the entire setup that we have shown earlier. This is the PCB, this is the result of monotone sinusoidal signal, and this is the result of music. In this section, we will discuss a few key challenges that we faced and our solutions and learnings throughout those. So first challenge was the bond wire parasitics. So almost till the end of the design cycle, we missed the parasitics due to bond wire, which were significantly high, in fact, higher than what the output switches were designed for. And hence the bond wire parasitic started to dominate, and we lost about 25% of our efficiency. So the workaround or the solution to this was basically dedicate multiple pins to this output switching driver path, so that multiple bond wires come in parallel and we get lesser and lesser conduction losses. By employing this methodology, we were able to get back around 25% of our lost efficiency. The second challenge that we faced was two stable states of the fully differential amplifier. So the fully differential amplifier had a zero stable state and a, desired stable state in the initial architecture, depending on where you feed the common mode signal. And then we had to improve the fully differential amplifier's common mode circuit architecture to have only one stable state at the output, and hence that mitigated this problem of fully differential amplifier getting stuck at startup. The last problem that we faced was post silicon. That was huge switching losses that we were getting due to the huge bond wire parasitics that we have shown already earlier. Uh, this huge switching losses used to couple to the references of the ramp generator, and the ramp generator used to glitch as shown on the left side. The workaround or the solution to it was basically putting a lot of decaps all around the surf board, all around the board, because the chip is sort of sitting inside, and then there is a package, and then there is a surfboard, and then there is the board, and the nearest decap that was placed earlier was very far from the chip. By putting these decaps as close to the socket as possible, we were able to suppress the noise a lot from earlier, and then we were getting clean ramp and hence clean output signal. We would like to uh, thank Columbia University and Apple for extending us this opportunity to be able to tape out chips as master students. It was an immense learning experience. We would also like to thank Professor Peter for his guidance and instructions throughout the entire project. We would like to thank our TAs Alfred, uh, Moore, and Hongzi for their help and support during the entire design and testing and bring up of the chip. Thank you, everyone.